What's going on, everyone? The networking guru here, and today we're going to be going over domain 2.1 of our Network Plus video series. So let's go ahead and get started. So in today's video, we're going to be going over basics of routing, learning what a router does, routing fundamentals, and then we're going to get into our routing protocols. We're going to get into static routing, dynamic routing, just the basics. We may get some CLI action in there, configuring static routes. But as far as the dynamic routing, we have to learn EIGRP, OSPF, BGP, so we're not going to touch CLI on that today. Then we're going to end this lesson going over how a router selects the best path. So that's three options we're going to go over, or how it selects the best path to place in the global routing table. So let's go ahead and get started. I'm going to move my face out of the way here. And again, we're going over domain 2.1, explain characteristics of routing protocols for our Network Plus video series. So here's our objectives. So we're going to go over static routing, dynamic routing, and route selection in today's video. And then in the next video, we'll go over other routing technologies like NAT, virtual IP, subinterfaces, and first hop redundancy protocols. Now, before we get into what static routing is, let's go ahead and jump to our whiteboard and let's go over the fundamentals of routing first. We'll have a nice network diagram on there and a couple different notes. Okay, so you see here we have our whiteboard here going over routing fundamentals. So what is a router's whole purpose? And when we go over this, I'm going to be explaining things from the perspective of router 2, R2 right here, okay? So a router's whole purpose is to send traffic based on destination IP address. That's its whole purpose. Meaning if I'm router 2 and I have users and they want to talk to a remote destination, meaning they want to talk to a server or someone not on our local area network, not sitting right next to me, not connected to the same switch, I need that router to route my traffic, to route my IP-based traffic. So what happens is a user, when they want to talk to a web server, they generate a packet. In that packet, we have all of our layers of the OSI model. Specifically, right now, when it comes to routing, we're worried about that layer 3 header in that packet. That layer 3 header is going to have a source IP and a destination IP. That destination IP address, when it comes inbound to the router from our user. So if we scroll down here, Bob here, he wants to talk to 192.168.3.24. So let me just say this is the destination IP right here. He's going to send this packet now, right? This is my layer 3 header, up to R2. R2 is going to look at the destination IP, and then it's going to reference its global routing table. The global routing table will decide where to send that traffic. And if we have a route in that global routing table for that IP, meaning we know where to send for 192.168.3.24, then we'll send it to the next hop. So if the destination IP is on a remote subnet, the routing table will have what's called a mapping of where to send that traffic. So that mapping will pretty much say, hey, I know where this network is, and it's on this next hop, or it's connected to this interface. If it does not have a route available in the routing table, that traffic will be discarded. So if we don't know where to send a destination IP that we receive from one of our users, we just discard it. Now, if we take a holistic look at this, or like a top-down look, R2 here, when it's building its routing table, before we even get into routing protocols that help build the routing table of all the unknown networks, right? We got to look at what router 2 automatically knows about. It's going to know about its connected routes. So here's its pseudo routing table here. That's why I put like quotations around it. R2. So what subnets does it know about? Well, it has this interface, gig 00, gig 01, gig 02, and gig 03. Those interfaces are all going to have a network. So you can see in its pseudo routing table here, before we do any configuration, before we enable any routing protocol or static route, we see its routing table. So it's going to know about this subnet, the 10.0.4.0/24, hanging off gig 0. So that's going to be local/connected. It is connected to R2, so it knows about it. It's going to know about 10.0.3.0, hanging off gig 01. It's going to know about 10.0.2.0, hanging off gig 02. And of course, it's going to know about its users in its local area network, 192.168.1.0/24. and that is also local and connected, hanging off gig 3. But here's the problem here, and here's what we need to fix as network administrators. It's great that R2 knows about all these shared Ethernet segments to its routing neighbors. But Bob here, if he wants to talk to Alice, well, he's going to create a packet destined for Alice's IP address here. So it'll be this subnet down here, 192.168.3.0/24. That's a remote network that R2 doesn't know about. So when this packet heads up to R2 here, R2 is going to look at that destination IP address, and it's going to say, hey, I have no idea where this IP address belongs, what network, So what am I going to do? Well, it's just going to discard that packet. So now as administrators, what do we have to do? We have to do some configuration. Now we're about to talk about static routes. So in a static route, we would go on R2 and we would type in R2 or on a GUI. I'm used to like Cisco CLI iOS when I train, it's just kind of easy. We would say, hey R2, if you want to reach this distant network, send traffic out gig 02. And once we configure that static route, it'll update our routing table. So for example, if I'm looking at the perspective of R2 right here. So if I come on R2 and I type in this command right here, IP route to 192.168.3.0, it's subnet mask, and I go out gig 02, that is me configuring a static route if this was a Cisco router. And if I did that, on this routing table, this would update. Let me update this for us. So this would update. Let me grab this box here. And say, hey, we know about 3.0, but this is learned via a static route, via gig 02. And that's pretty much saying that's the exit interface. Okay? So that's one way we can now tell that router, hey, this is where you're going to head for that static route, okay? Because of that static route we put in there, right here, this static route, now Bob can talk to this destination network. And that's routing fundamentals in a nutshell. Routers build routing tables that determine the path to a destination network. Now, sometimes you'll hear this called a prefix as well, a prefix. So this is a prefix that we know about. It's the same, it's synonymous with network, distant network, okay? Now that we learned about our routing fundamentals, let's go into our PowerPoints and let's go over static routing and some key features of static routing. Okay, so back to our slide here. So static routing. This is a simple form of routing where a network administrator manually configures the routing table on each router. In static routing, the route to a specific network or device is explicitly defined. This means that the router always sends traffic to a pre-configured path, regardless of network changes, failures, or congestion. This will make more sense when we get into dynamic routing. Essentially what we're saying here is that when I go into a router and set a static route, no matter what happens, even if the link I'm sending traffic on for that static route dies, it goes down, we're still going to attempt to send, okay? It's a manual configuration to reach a destination prefix or network. So some key characteristics of static routing. There's manual configuration. So in a small environment, that works. As you can see here, we have this stub environment here where you can look at R1 as our customer edge router, so our router that's connected to the ISP. So really we have one configuration here. Send to the ISP. That's it. So luckily, that's an easy configuration for us. And we configure a static route called the default route that just says send out to R2. But if I come back to my whiteboard here, this is a lot of manual configuration for R2. I have to make a static route to here, and to here. Now, you may say it's only 3 commands you got to do. Just do this IP route 3 times. But I got to do that on R1. I got to do that on R3. And I got to do that on R4. So it can get really complex with this manual configuration. But it's simple, it's easy, and it's reliable. No adaptation to changes. So if a link goes down, the router will not automatically switch to another route unless manually configured to do so. So this isn't talking about an advantage, really. This is saying, hey, you kind of lose out on this adaptability when you do just static routing. There's low overhead, though. There's not CPU and a lot of compute resources involved in static routing, like there would be for dynamic routing. It's best used for those small, simple, and highly stable networks where routes don't change frequently, and the best example of that is like a stub network. A stub network is when a router has no downstream routing neighbors, meaning it's simple, it's what you have at your house, it's what I have in my small business. I have my router, on one side is my ISP connection, on the other side is my users, and that's it. So one static route will do for that. Now, as we get complex and we start making IPsec tunnels, and maybe we become part of a hub and spoke topology, or maybe we do add a routing neighbor, then we might look at doing dynamic routing. Some other static routes that I just want to talk about, these aren't on the exam objectives particularly, but I want to talk about them, is a floating static route. This is using a backup, so having a backup route using static route configuration. So imagine we have like an OSPF, that's a dynamic routing protocol we're about to learn about, a fiber uplink here, and we have a backup static route down here. We can configure that by changing the static route's administrative distance to something higher than the dynamic route. Again, I don't know if this is on the exam or not. I didn't see it in the exam objectives, but I just wanted to talk about it because it may be something you see in the real world. Then we have a host route. So this is a static route that will route traffic to a singular host, meaning that if we have this primary link and we're talking to this server farm over that primary link. So here's our static route configuration. Hey, or IP route to 172.16.0.0/27 over this primary link. But when I talk to this specific server here, .3, this server right here, .3, I want to use that secondary route. So that's a host route where you're routing traffic to a single IP address. Okay, now let's move on before we get too complicated. So before we jump into dynamic routing, let's go ahead and do some configuration. I'm going to go into my EVE-NG environment. This is my network emulation software that is emulating Cisco IOSs. And let's do some actual static route configuration. So I'm going to transition over there. I'm going to pause the video real quick. Okay, so here we can see my network environment here. So I have R1, R2, and hanging off both these routers is 3 different subnets. So my users over here in R1 want to talk to my users over here hanging off R2. So let's console into these routers and configure some static routing. So you see I'm consoled in right here. I'm in R1. And what I'm going to do actually is I am going to zoom my face out. And I'm going to drag R2 over like this. I'm using Secure CRT. If you've never seen Secure CRT, there's a lot of features in this software here. It's called a terminal emulation software. This is what we use to console in, it's SSH in, to CLIs, terminals, things like that. Okay. So I'm going to get into both these routers. I'm going to type in this configuration, show IP interface brief, and I'm going to make sure that all of our IP addressing is good. Now, again, this is not going to be on the exam, or at least it's not part of the exam objectives. If you want to skip ahead to back to the lecture to take your notes, to go through this quickly, because you just want to cert out, you don't care about learning real world stuff, please feel free to skip ahead. I'll put a little a timer up here so you can hit the direct link, right, of when we get back to the PowerPoints. But okay, here we go. So all of our IP configuration is set. So I'm going to go on both these routers here, and I'm going to do a quick ping test. So from R1, I'm just going to ping my neighbor. Obviously, okay, so there we go. So R1, this is its IP address on the point-to-point link to R2. I did a ping test over to the other side. I just want to make sure there's network connectivity between our routers. I'm going to come back here to R1, and I'm going to do another ping test. Do ping 192.168.10.1. So I can reach the other side, okay? Now, I can reach that other side because when I do that ping test, the source IP is coming from R1. But if I do that ping test again, and I source it off gig 01.10, my sub interfaces can reach there too. So if I do show IP route, do show IP route. Here's our routing tables here, okay? So we have no configuration there yet. So let's go ahead and configure some static routes. So at R1, I'm going to do IP route 172.16. And I'm going to come back here and look at what we got here. .10.128. And this is a /25. And I'm going to say exit interface gig 00. And I'm going to do this again. I'm going to hit up arrow. And now I'm going to go to 20.0. And this is a /24. Out gig 00. So that is how we configure static routes. So we do it on the other side. We'll type in IP route 192.168. We come back up here. Let's see what we got. So we can just do like a summary here. We'll just say to reach both those subnets, we'll put a /24 out gig 00. We'll hit the up arrow. And if we want to hit the 20 range now, 20.0, it's going to be the same thing, out gig 00. Now on both these routers, if we type in do show IP route static, we can see our static routes. And now we'll have full reachability between each other, okay? You can see that S here, that S code means it was a static route. Alrighty, so now let's get back to our PowerPoint. Okay, so dynamic routing. So we just talked about static routing, and you know, a routing fundamentals, the whole purpose of a router is to send traffic via IP-based traffic. So looking at a destination IP, referencing our routing table, seeing if we have a route or a path or a mapping to that destination IP, and if we do, sending that traffic to wherever that mapping is. If it's, hey, the next hop IP address is this, or this is your exit interface. We understand that. So really the key piece here is that routing table. We'll have users sending traffic. The router needs that global routing table to tell it where to direct that traffic. So how do we build that? Well, we can do static routes, which we just learned about, or we can enable dynamic routing. So dynamic routing is going to be used when we have big systems with lots of routing neighbors and it meets a use case. So we have two different types of dynamic routes. We have IGPs and EGPs, interior gateway protocols and exterior gateway protocols. IGPs, for your network administrators, your junior network admins taking this course, are probably going to be your bread and butter. You'll have to learn OSPF, maybe EIGRP, to do routing within your autonomous system. An autonomous system is really your domain at your organization. So you may have Spectrum, Metronet, AT&T, wherever you live, wherever you're watching this, you have your local ISP, your internet service provider. Well, when it comes to that service provider talking on the internet, we call that an autonomous system. And that autonomous system it's an entire routing domain, but it's also an ISP, it's an organization. When that ISP needs to communicate to other ISPs, we use something called an EGP, okay? So when we're doing routing internally, within our system, within our domain, within our enterprise, within our autonomous system, we use an IGP, an interior gateway protocol. When that autonomous system, that ISP, that enterprise needs to talk to another enterprise, another NSP, ISP, another autonomous system, we use an EGP, an exterior gateway protocol. That EGP protocol we use is called BGP, Border Gateway Protocol. BGP is the only EGP available that we use. BGP is the Internet Routing Protocol. Now, it is a routing protocol, and as much as I love to dive deep into this, we need to just go over the highlights so you understand on a Network Plus exam what it does. We're not going to dive deep into configuration, all the nuances on it, how it actually is TCP based, and it's more of an application than a routing protocol. We won't touch that. We're just going to go over the notes here. So the first dynamic routing protocol we're going to learn about is BGP. Now, all dynamic routing protocols, there is administrator configuration, but then beyond that, the routing protocol is intelligently creating our routing tables and talking to neighbors. So BGP. BGP is a path vector protocol that operates across the internet, managing the routing between autonomous systems. BGP is known as the protocol of the internet because it is used by ISPs, internet service providers, and large organizations to route traffic across different networks. When we say networks, we mean autonomous systems. So it's an EGP, an exterior gateway protocol. BGP uses attributes like AS path or next hop and policies to determine the best path. So another thing about dynamic routing protocols, guys, is each routing protocol is going to have its own metric. So whether we're talking BGP, OSPF, or EIGRP, they're going to have their own algorithm and metric to determine the best path. So with BGP, its path selection is based off the autonomous system path, next hop, and other BGP attributes, what we call it, to determine that best path that we won't get into here. Okay? But if you're taking notes, all dynamic routing protocols have their own metric. Okay? And that metric is going to come into play when we build the routing table and select the best path. We'll get to that. Okay, so BGP. It has a few steps in establishing a BGP connection. First is going to be that neighbor relationship. And that neighbor relationship is going to be something that's unique for each routing protocol, but each routing protocol has to establish routing neighbors. Here's how BGP does it. So eBGP neighbors or peers are manually configured to establish a TCP connection using port 179. Neighbors are typically directly connected, but can also use loopback interfaces with the appropriate update source configuration. What we're saying here is that we establish BGP neighbors using TCP. So what that really means is that R1, and let me zoom my face out here, and R2 here could be geographically separated with like 10 routers in between. And as long as we have TCP IP reachability, we can establish BGP peering. So once we begin our neighbor relationship establishment, really we're doing a TCP session establishment. So after we configure who our neighbor is going to be, because we'll go in and configure, each peer sends a BGP open message to initiate the session. Now that session, open sent, open confirmation, and we become established. After this establishment, so now we have a TCP connection and a BGP connection, we're going to exchange routing information. So once we're established, now we send updates. So we're going to be sending BGP routing tables using update messages, BGP update messages. Now once those messages are sent, we get a BGP routing table, and then we put those routes into our global routing table. And that's as far as we're going to talk about BGP. The next dynamic routing protocol we're going to talk about is EIGRP, the Enhanced Interior Gateway Routing Protocol. Now notice, I am only going to go over the routing protocols that are on the exam objectives. So that's BGP, EIGRP, and OSPF. But there are others like RIP, ISIS, that we'll talk about in our next whiteboard session. So EIGRP is another dynamic routing protocol. This is an IGP, an Interior Gateway Protocol, meaning this is going to be for routers sending routing updates within an enterprise, within a domain, within an autonomous system. So again, it stands for the Enhanced Interior Gateway Routing Protocol. This is an advanced distance vector routing protocol. It was created by Cisco and really was proprietary for the longest time, but now there's a IEEE standard for it where other vendors can adopt it, but it's not really done. It's still kind of a Cisco protocol. EIGRP uses the dual algorithm called the diffusing update algorithm as referenced in the loop-free routing using diffusing computations. Whew, that's a mouthful. This was RFC 7868. So if you ever want to see how EIGRP determines the best path from EIGRP learned neighbors, it uses the dual algorithm. You can read about it. So EIGRP is a dynamic routing protocol that creates a loop-free path to destination networks based on what's called the best metric. So EIGRP's metric is going to be determined by something called K values, which we'll talk about in just a second. Now, establishing EIGRP routing domains. So the first step is going to be establishing neighborship, like all dynamic routing protocols. EIGRP-enabled routers will initially send an EIGRP hello packet. So we have R1, we have R2. They want to establish EIGRP neighborship. They're going to send a hello packet. If the K values match and the autonomous system number match in that hello packet, we have these fields that have to match between all our EIGRP routing neighbors. If they do, they're going to become EIGRP neighbors. Once neighborship has formed, EIGRP will send hello packets at intervals of 10 seconds and hold timers or dead timer packets at intervals of 40 seconds. After not hearing from a neighbor in 40 seconds, we consider that neighbor down and dead, and we no longer have that neighborship. EIGRP will maintain a neighbor table, and then from that neighbor table, we will build a topology table. So this is getting into how a routing protocol like EIGRP begins to build our global routing table. So EIGRP will build a topology table from its EIGRP neighbors using information from its neighbors' update packets. So step 1, we establish neighborship through hello packets. And in those hello packets, we have K values, autonomous system numbers that have to match. If those match, we become EIGRP routing neighbors. Once we're neighbors, we send routing updates. Those updates build an EIGRP topology table. And once that topology table is built, we execute the dual algorithm. And that dual algorithm will then select the best paths to place into the routing table. Whew. Okay, now let's take a little breather here. The next routing protocol we're going to talk about is OSPF. So OSPF is another IGP, Interior Gateway Protocol. The OSPF protocol is what we call a link state routing protocol, meaning that we're going to be sending routing updates based off our link states. Now, OSPF has the same general, sequence to building routing tables and building a converged routing domain. So OSPF enabled interfaces, when we go in and configure OSPF on our routing neighbors here, R1 and R2, they also are going to send hello packets. And in those hello packets, there's going to be parameters that have to match. These parameters are the hello and hold timers that have the same function as EIGRP, hello timer sending every 10 seconds, and a hold timer every 40 seconds that says, hey, if I don't hear from you in 40 seconds, I'm going to consider you down. Those timers have to match in OSPF. We're also going to send an area ID in our hello packet. That area ID has to match between directly connected neighbors for neighborship to form. The maximum transmission unit, so that's at default 1500 bytes on each link, has to match as well for OSPF neighbors to come up. So after OSPF enabled routers send hello packets and those parameters match, we form neighborship. And now we have that OSPF neighborship table. Once that's established, now we start sending our routing updates. So we call these LSAs, link state advertisements. So now we start sending link state advertisements to our neighbors. Now I have a 2-hour video on OSPF if you ever want to go watch that, guys, because I'm trying to keep it as brief as possible. But once all LSAs are sent between routing neighbors, OSPF is going to fully converge, meaning every router in an OSPF routing domain or area is going to have a shared and synchronized link state database table from all those routing updates. Now, once we have that and our network is what's called fully converged, OSPF is going to execute this shortest path first algorithm. That algorithm is going to be a bandwidth-based metric. And the best paths based off that SPF algorithm that's executing on our topology table in our link state database is going to select the best routes to put into the global routing table. So here we have it. Once all LSAs have been flooded, the link state database is fully populated, the SPF algorithm will be executed. The metric is a reference bandwidth, which means reference bandwidth divided by actual bandwidth in OSPF is going to give us our cost or our metric. And then once the network is converged, we put the best routes into our routing table. There's going to be no periodic updates. LSAs are only sent again if there's a topology change. So meaning once we're fully converged and all of our link state databases are the same and we put the best routes into our global routing table using OSPF. Now remember, this is OSPF doing this routing protocol. We're not going to send any more updates. Okay. Whew. Now I know that was fast. For the exam, let's just, again, cover some basics. EIGRP and OSPF, they are interior gateway protocols, okay? EIGRP uses the dual algorithm. OSPF uses the SPF algorithm, shortest path first algorithm. The OSPF metric is determined by bandwidth, okay? BGP is an exterior gateway protocol used to route between autonomous systems. EIGRP was Cisco proprietary, and OSPF is open source. I think I might have missed that in the slides, meaning it's always been open and any vendor can use OSPF. It's vendor neutral. Now, for the last section of this video, so I don't have a 2-hour long video on routing, let's go over route selection. So I'm going to bring this back to our whiteboard, and then we'll finish off the slides and we'll do our quiz. Alrighty, so we're at our whiteboard here. So now that we've gone over kind of the basics of routing, the different routing protocols, now we need to kind of define our routing table a little bit more. I want to go over how to read a routing table, and I want to go over also how we select the best path, the best route to place into our routing table when we're learning about multiple destinations from multiple paths, multiple routing protocols, and different prefix lengths, okay? So, selecting the best route. So every device has a routing table that determines the best path for IP-based traffic. What we're saying here is that if you have a computing device that sends IP-based traffic, even your local Windows machine has a routing table. It's just a default route out. But when it comes to actual routing, that global routing table determines the best path for IP-based traffic. We know this from our basic routing principles. Now we have 3 rules when determining how to send traffic and putting the best route in our routing table, okay? So 2 things there. Where do we send traffic? What's the preferred path for destination IP-based traffic? And how do we select the best path when we're learning about the same destination network from 3 different or 4 different or 2 different routing neighbors? So we have 3 rules here. When it comes to building the routing table and selecting the best path to send our IP-based traffic, the first rule is the longest prefix will always be preferred for duplicate paths to the same destination. Now let's break that down. 1, what is a prefix? This always confused me when I first started learning about networking. I've heard of subnets, networks, broadcast domains, destination networks. Destination network with the subnet mask with the CIDR notation is a prefix. If I take my pen here and I say, what would you call this? And you said that's a network or a subnet, you're correct. If you also said that's a prefix, that's also correct. When you read about the rules to selecting the best path in a routing table, they call it a prefix, okay? So the longest prefix will always be preferred for duplicate paths to the same destination. If we break down our little diagram we have up here, we have R3 and R4, and we're working in R2. R2's global routing table is going to have 2 networks here, 192.168.0.0/25 and /24, learned from 2 different paths. The longer prefix out of these 2 is this /25. So longer prefix refers to the higher CIDR notation, the bigger number in that CIDR notation, okay? Now, the second rule, and we're going to break down our routing tables a little bit more. We're going to do examples of this. The second rule, let's say our prefix lengths are the same. So what do we mean here? Let's say that this is actually a /24. So now the prefix lengths are the same. What is our tiebreaker? Now how do we determine, what is actually the best path here and the best route? So if this is the scenario here, we're going to go off something called the administrative distance. So the administrative distance is a number 0 through 255, and the lower number is better, and the administrative distance determines the trustworthiness of that route, with the lower number being more trustworthy or better. Each routing protocol, from static routing all the way to routing protocols like RIP and ISIS, which we haven't talked about, all have an administrative distance that's preset, and it's part of their standard, right? So when you go read an RFC about a routing protocol, the administrative distance is preset, with lower being better, okay? Now, if this is the scenario here, we're learning about the same prefix length, the same destination, the exact same destination, via EIGRP and OSPF. EIGRP, according to our chart up here, has the lower administrative distance. So guess what? This is going to be the preferred path, and that's going to be the only path in our routing table. Well, just depends, but That'll be the path in our routing table. Okay, now let's say we have this scenario where I take our OSPF learned route and I actually configure EIGRP. Now, if this is both EIGRP, now we go based off the lowest metric. So if this was the scenario, let's say this was fast Ethernet, because EIGRP's metric is based off bandwidth and delay. So to make this accurate, let's say this is fast Ethernet, this is gig, with gig being, 1,000 megabits per second, fast Ethernet being 100 megabits per second. This is going to have the higher metric, our path learned from R4. So now in this global routing table, which is going to be the preferred path? It's going to be this one with the lowest metric. So our tiebreaker, if we're using the same routing protocol and our administrative distances are the same, is going to be the lower metric. Okay? Now this probably wouldn't even be in the routing table because of how high its metric is. Okay? Now for all you network engineers that understand EIGRP's reported and feasible distance, refer to my CCNA course if you want to learn why that wouldn't be in the routing table. But this would be the preferred path right here. Okay, so those are the three rules. Now, let's take a second, look at an output of a Cisco routing table and kind of define it, what we're looking at here. So I'm going to scroll down here, and I got this screenshot from the Cisco Press website. So they're looking at a routing table in this router R1, and let's kind of break this down. Let me erase this. Okay, that'll just stay there, I guess, that little mark. So in this routing table, we can see we have our C codes and our L codes. So our C codes and L codes, this means local, and the C means connected. So locally connected, okay? This R right here, that means it was learned via RIP. So these codes right here is how you learned about a route. Now this right here is the actual destination network, or guess what? Our prefix. This is going to be the administrative distance, this is the metric, and this is the next hop IP. Let's clean it up a little bit. So this is what a routing table looks like. So when a router receives a packet from its users and it inspects the destination IP in the layer 3 header of that packet, it's going to reference the routing table to see if it has a path, if it has a route in the routing table to send that traffic. Up here, this is called a default route, guys. So pretty much this will always have a path somewhere, but we have more specific routes down here, which we're about to get into after we break this down. Now, I got this from the Cisco Press website as well. This is just a single route here, breaking it down more. That R right here is the route source. So that R equals RIP. If it was an O, it'd be OSPF. If it was a D, it would be EIGRP. Right here, we have the destination network. That's also our prefix. In these brackets, the first number here is the administrative distance. So RIP, the administrative distance is 120. We'll go over that chart here in just a second. And then the next number is going to be the metric. Each routing protocol has a unique algorithm for their metrics, as we know. With RIP being a distance vector, it goes by hop count. This is the next hop IP, meaning that if I have R1 here, I have R2 here, and they're connected. And in the middle here, they're 25000/31. And right here is .1. And this is R1's route. So this is R1's routing table. The next hop is going to be this router 2's IP address. So we're routing neighbors of R2 on this subnet. And the next hop, how we communicate to R2, is via this IP address .1. That's the next hop, okay? With the outgoing interface being our local outgoing interface, where we actually send traffic out of, okay? So that's how we read a route. I don't know what this number is here. I'll just delete that. Okay. Now, guys, let's look at these administrative distance table here. So take these notes if you want. These are the basic routing protocols I want to put up here. Static routes are still a routing protocol. Their administrative distance is 1, so they have the best administrative distance out of all the routing protocols. Now remember, administrative distances are 0 through 255. They determine the trustworthiness of a routing protocol. The trustworthiness of a routing protocol. And lower is better. Now here we have eBGP is 20, EIGRP is 90, OSPF 110, ISIS, another link state routing protocol that's not in the exam objectives, but I wanted to put it in there, is 115, RIP is 120, and external EIGRP, which if you ever want to learn about, go to my CCMP course, is 170. So out of our IGPs, remember BGP is an exterior gateway protocol, which as a junior network admin, if you're messing with BGP, you're getting underpaid. But our IGPs that we could mess with as a junior network admin, which are these 4 right here, EIGRP, OSPF, ISIS, and RIP, EIGRP has the best administrative distance, okay? And then, of course, static routing is 1. All right. Now, I could probably end this here, but I want to do some practicing with you guys. Let's actually go through selecting the best route. So let's take a look at this routing table here, and I'm going to put it to what it should be based on our diagram, okay? So we look at our diagram here. We have R2's routing table. It's learning about 2 prefixes here. 192.168.0.0/24 from R4, and this is learning it via OSPF, and this is on gig port 0/2. And this is learning from R3, the 192.168.0.0/25 network from R3 via EIGRP with outgoing interface being gig 00. So this is the global routing table we're going to reference when we get packets inbound from our users. So Bob here wants to talk to this destination IP. This is the layer 3 header of the packet that Bob has created. So the 192.168.0.24 is a destination IP. So when R2 receives that destination IP, it's going to reference our routing table. This is a /25. Now, if I ask you, is it sending it out gig 01 or gig 02? More than likely, you're going to say gig 01 based off the administrative distance. But, that's not our first rule. The router is actually going to send it out this route based off what? The longest prefix length, okay? The longest prefix length. So, a /25 is longer than a /24. So we would say, as the router, hey, 192.168.0.24, that destination IP fits within both these subnets. However, /25 is a longer prefix, so we're going to send it out this path, out gig 01, no matter what. Okay? Now let's change it up a little bit. Let's say now our user wants to talk to 140. Now where's it going to send it? Well, 192.168.0.0/25, does this IP address fall within there? No, it does not, because this range /25 is .0 through .127. So .140 is out of its range. So actually, we're going to go with this OSPF route because this destination IP address falls within this subnet because the /24 is .0 through .255. Okay, hope that makes sense. Now let's change it up again. So let's say this is a /23. So now we're learning about this /23. And now our network range is .0, .0 through .1.255. We're getting into that third octet here. When R2 receives this request, 192.168.0.140 is a destination IP that I need to route traffic for. That falls within both these subnets, this /23 and this /24. But now which one is the longer prefix? It's this OSPF learned route. So even though OSPF has a higher administrative distance, that does not matter. Because when we're determining the best route, the best path to send on, the very first rule is the longest prefix will always be preferred for duplicate paths to the same destination. that IP address belongs to both these prefixes. But which one is longer? Now it's our OSPF learned route. Has the longer prefix, so that would be preferred even though the administrative distance is better on this EIGRP learned route. Because our very first rule is the longest prefix will always be preferred. Awesome. Now let's change it up again. So let's say this is OSPF. We're learning both /24s here. And in this environment, this would kind of be like this, guys, where we have like this shared connection. Okay? Something like that, right? Shared connection. Maybe we got some FHRP going on here, which we're going to learn about. And we're learning about this via OSPF. Now, remember OSPF. Remember its metric is based off bandwidth, okay? So let's say this is an Ethernet port. So 10 megabits per second. And let's say that's our destination IP. Now, we go down our tiebreakers, our rules here. They have the same prefix length. This is /24. The lowest administrative distance doesn't matter because they're both 110. So what's next is going to be the metric. So that's this second number in our brackets here. Now we're going to go based off the lowest metric will be preferred. So in this scenario, we're learning about 192.168.00/24 from both R3 and R4, both via OSPF, but from R4, we learned about that on an Ethernet port. So that bandwidth is way slower, so the metric or cost will be way higher, which means worse. So now in this scenario, we're going to go based off this path, out gig 01, because of the better metric, the lowest metric or cost. All right. Now, if that doesn't make sense or if you want more practice doing that, just keep replaying that section of selecting the best route. But now we're going to move on to our quiz, and we're going to finish up this video going over routing technologies. All right, awesome. So let's do our quiz. I'm at our learning management system here, our academy, and let's go ahead and click on our Network Plus course. I'm going to go to our correct lesson. We're in domain 2.1, routing protocols. Scroll down here, and let's go ahead and take our domain quiz. This will be a quick 3-question quiz here. So question 1, which metric is used by OSPF to determine the best path to a destination? So kind of a tricky question here, and that's why I like this one. I just taught you that the lowest metric is the best path when we're deciding between the same routing protocol and the same prefix length. But what do we call OSPF's metric after the SPF algorithm is done? We know it uses bandwidth. It uses bandwidth in that measurement to determine the best metric. We call it cost, okay? It's called cost in OSPF. That's the actual term we use in OSPF. Say, hey, that path to R2 has the lowest cost. We got that cost using bandwidth. Bandwidth is the metric we use to determine the lowest cost. That is something specific to OSPF. Question 2. Which dynamic routing protocol is most commonly used for routing between autonomous systems on the internet? So that's going to be our only exterior gateway protocol, BGP, the border gateway protocol, which is used for internet routing. Pause the video if you'd like to read the explanation. Question 3. Which of the following is true about static routing? That's going to be that it is manually configured. We configure the static routes. Pause the video if you'd like to read the explanation. Awesome. That is 100%. So I want to thank everyone for viewing. Please like, subscribe, share with your friends. Thank you for the support. And I'll see you in the next video when we go over routing technologies like FHRP, NAT, virtual IP addresses, and sub interfaces. Thank you.